And the best interpolation over discontinuity is actually piecewise constant. And here, though, the piecewise constant, best piecewise constant interpolation is actually not nearest neighbor. Why is it not nearest neighbor? Because we actually know when we have a discontinuity, which direction is the discontinuity moving, right? Okay, so if I only know the two cells like that, and presumably I would have a discontinuity right across the cell interface, right? That's the best guess I can have. And now, if I know the shock wave is moving, if I know the discontinuity is moving towards the right, which side of the flux should I use? From the left, right? Because I know, okay, even at this moment, the discontinuity is sitting on the interface between the two cells. Immediately after epsilon amount of time, the interface is going to be in the right-hand side cell, and the value at the interface now is going to be the value at the left cell, right? So I should actually be taking the value from the upwinding direction of relative to the movement of the shock wave. Okay, so that's actually the motivation between the upwinding scheme. So let me just say a little bit about the upwinding scheme. So basically, by doing a piecewise constant interpolation, we are reverting back to a first order scheme, right? So if I actually have a smooth solution, using upwinding basically gets me back to first order. That's actually not what I want in smooth regions. So most real finite volume solvers, they have to detect shock waves. And whenever they detect shock waves, use something like an upwinding scheme. And whenever a shock wave is not present, go back to something like the central average scheme. Right, so that's kind of the general strategy. But now let's first aim to get a scheme that actually works for shock waves. All right. Okay, so the real question we want to focus here is if we have two cells and we only know the cell average, right? So cell average here, cell average here. How can we compute the flux at I plus half? So the upwinding scheme says the flux at I plus half should be either Fi or Fi plus 1, right? Which is equal to F, the function, the flux function evaluated just on the cell averages. If the shock wave is moving left or right. So I'm going to be taking the left value if the shock wave is moving towards the right. And how do we tell? How can we tell if the shock wave is moving towards the left or right? Yes? Yes. Basically, the speed of the shock is a generalization of the speed of the wave, right? If you look at the conservation law, again, if you look at the conservation law, the speed of the wave is df dw, right? That's my u. And the shock wave is has a speed of delta f over delta w. So here, if the fi plus 1 minus fi divided by wi plus 1 minus wi greater than 0, right? Then the shock is moving towards the right. If it's less than 0, the shock is moving towards the left. Okay? And usually it doesn't matter if you put the equality sign on either up or down, because the likelihood that is exactly equal to 0 is very low, right? Although we are actually going to see this case here. So let's try to implement this in MATLAB then. Okay, so now I have the flux, and let's compute the shock speed or wave speed, right? Wave speed if there is no discontinuity. It's the same formula. Okay, so Oh, actually, for that to happen, I first have to compute Fi. Well, actually, let me just move this line to here. Fi plus 1, then speed is equal to Fi plus 1 minus F divided by Wi plus 1 minus W, which I haven't computed. So I need to do here. So Wi plus 1 is equal to W and W. All right. Okay. So if you are actually doing writing a real solver, I would be very careful about just writing it like that, because I would possibly get a name, not a number, out of this division, right? So if I have let's say if I set my initial condition to be a constant, all my W's are the same. By this subtraction, I get 0, and I get 0 divided by 0, right? So basically, I want to say, I don't remember the MATLAB. Is it this? Okay, so hopefully that works. Oh, actually, I don't want to say not. Actually, I want to order names. Or actually, let me just say is finite, because it's potentially I would get infinity by dividing. No, I shouldn't get any infinity, right? I should only get names. But anyway, so I should that works. So now I have computed the shock, and now instead of interpolation with averaging, I do a piecewise constant interpolation. So let me just set this as Fi plus 1 would be, okay, so let me actually look at the formula here. So I would be taking Fi if the speed is positive, and I would be taking Fi plus 1 if the speed is negative. So let's just say equal to F for now, and Fi plus 0.5, so would be equal to Fi plus 1 if the speed is negative, is equal to Fi plus 1 as negative, right? So this is basically assigning, this is a Boolean indexing. So this s less than 1 is going to be an array of true or falses. And this assignment is assigning whatever that is true, yes?
Here, I should have a dot for the division sign.
Oh yes, I should have a dot for the division sign. Otherwise, MATLAB would be trying to do matrix inversion, which doesn't work. Yeah, thanks. Okay. Flux accumulation shouldn't change, right? Anything else should stay the same. So let's run it to see if we make a mistake or not. Let's make another figure and plot the original solution, right? Initial condition. Hold on. Oh, now we shouldn't call it central flux anymore, but like it's already coded up, so let's still do that. Okay, so here is our solution. Okay, we no longer see oscillations, right? And basically it captures the discontinuity over here, which hasn't really which basically is going to develop further. Let's actually see if we evolve it a little bit more, right? So basically it already collided further, so basically we are fine with the solution. Yes?
Is it that the peak seems to be decreasing? Is that due to truncate?
That's a good observation. So if you look at the blue peak actually has decreased a little bit, right? So that's the result of a first order scheme being applied to the smooth region. And if you remember, like if we apply a first order scheme, the eigenvalues turns out goes into the negative real region, right? So basically we would be decreasing all the wavelengths, okay, all the different wavelengths, and that the result is the blue the solution has been smoothed out in some sense, right? So this is a prime motivation of actually having a shock detector and apply this kind of a first order scheme only when a shock wave is present, and use a second order scheme elsewhere.